talk about inverse functions. Before we can talk about inverse functions, we have to talk about what it means for a function to be one-to-one. A function is one-to-one if each x value corresponds to only one y value and each y value corresponds to only one x value. We already have a criteria for a relationship to be a function, right? Each x corresponds to only one y, but now we're adding the criteria in the other direction that says that each y must also correspond to only one x. So basically I have one x paired with one y. There's no doubling up on either side. To test if a graph is a function, we do the vertical line test. We're going to add to that the horizontal line test, which works in the exact same way, except now we're going to apply a horizontal line to the graph. So if any horizontal line will intersect the graph in no more than one point, then that function is one-to-one. So here are three different graph shapes. So we want to test to decide, is it a one-to-one function? So the first one is a parabola. So we should ask ourselves really two questions. First, is it a function? And I would say yes to that, right? And it's definitely a function. It passes the vertical line test. Any vertical line that I would draw through this function would touch only once. Is it a one-to-one function? To that question, I think we could say no, because if we apply the horizontal line test, the horizontal line is going to touch the graph in two places. So it is not one-to-one. Okay, what about the sideways parabola? Is it a function? The answer to that is no, right? It doesn't pass the vertical line test. If it is not a function, it is automatically not one-to-one. Because in order to be one-to-one, it has to pass both tests so that it can satisfy both of these criteria that we talked about at the top. And so if it's not a function, it's automatically not one-to-one. Okay, over here we have the cubing function, y equals x cubed. Is it a function? I would say yes. Passes the vertical line test. Is it one-to-one? I would say yes. It passes the horizontal line test. So y equals x cubed is a one-to-one function. For each x, I get exactly one y, and there's no chance for me to use two different x's and get the same y. That's not going to happen either. So for each x, I get exactly one y. Okay, so now that we've talked about what it means for a function to be one-to-one, that's a criteria for finding an inverse function. So now let's look at inverse functions. Okay, so what are inverse functions? Inverse functions are two functions that perform opposite operations. Maybe one function adds 5 and the other function subtracts 5. Right? Those would be opposite operations. A function must be one-to-one in order to have an inverse. So that's part of the criteria and why we would take the time to look at what it means for a function to be one-to-one. Functions f and g are inverses if, when we do the composition, f compose g of x, we get x, and g compose f of x, we get x. Basically, this is saying that each function is the opposite of each other, right? So when I do the composition, I essentially apply the two functions back to back in succession. So if I take this x, I apply g to that function to that x first, and then I apply the function f, and the operations of f counteract the operations of g, and so I get my same x back as a result. Likewise down here, I start with an x, I apply the operations of f, and then I apply the operations of g, and the operations of g counteract the operations of f, and so I get back to my original x that I started with. Okay, and then the inverse of f of x we write as f inverse of x. This is not an exponent, even though it looks just like an exponent. Remember, f is the name of the function. So this is just saying that this -1, it's not an exponent, this -1 here represents the fact that it's an inverse, or the opposite. Okay, so let's look at an example. We could ask the questions, are they inverse functions? So here's two functions. We could test to see if they're inverses. I want to do this informally first, just to give you an intuitive idea, and then we'll do it formally with the composition. That's the formal way to test that they're inverses. Okay, informally, we could just think about what operations each of these functions are carrying out. And the best way to do that is to just think about what would happen if I plugged a number in for x and I wanted to evaluate the whole function, right? So if I plugged in, let's say, x to be 2, what would I do to that 2 to evaluate this expression? Well, first I have 2 cubed, so I would cube it. And then once I got 2 cubed, I would add 1. Okay, we're not plugging in 2, we're just thinking about what would happen if I plugged a number in for x, so I could think about what operations f carries out. Let's do the same sort of experiment for g of x. If I were to plug a number in here, let's say a 2 for example, what operations would I apply to that 2? First I would subtract 1. And then once I subtracted 1, then I would apply the cube root. Can you spot the opposites here? The function f cubes, the function g cube roots. The function f adds 1, the function g subtracts 1. So not only though do I have opposite operations, but I also have those operations in the opposite order. And I like to use this shoe and sock example to kind of explain this, right? If you were to put on your shoes and socks, you would first put on your sock, and then you would put on your shoe. If you wanted to undo that whole process, you would have to first undo the last thing you did. So you'd have to take your sock, or your shoe off first, because that was the last action you took, and then you would have to take off your sock. And that's sort of the same idea here. So yes, I would say these are inverses, right? Informally, we can see that in the operations that they carry out. Okay, formally, we would form their composition. So let's take a second to do that. And I know we've practiced this in another video, but these topics in this material for test 3 are definitely interconnected. And so this is one of the ways. Okay, so we could look at f compose g of x. This is f of g of x. So basically I'm going to take the function g and place it as a substitution for the x here in the function f. So I'm taking the function f and I'm substituting the function g, which is the cube root of x minus 1. Here's the function f, sort of its shell. I've taken out the x. Okay, so I'm going to use the function g here as my input for the function f. these two functions are inverses, then we should be able to make some nice canceling, right? Because their operations should counteract each other. And you have to do this carefully. Sometimes we get a little bit too excited and we just start canceling things out. We do have to kind of make sure that they do in fact cancel. Sometimes they look like they cancel and they don't. So you might want to just be careful as you're doing this. This one does, right? The cube and the cube root, those can cancel each other out. So we'll have x minus 1 plus 1. And then minus 1 and plus 1, those add to 0 or cancel each other out. And we're left with just x. So this says that f counteracts the actions of g. This is a two-sided justification, I guess. So now we need to show that g compose f of x does the same thing. This will be showing that g counteracts the operations of f. So this is g of f of x, which means we're going to substitute the function f into the function g. G takes the cube root of the input minus 1. We're using f of x as our input. Okay, same thing here, right? We're looking to see if maybe the operations cancel each other out. I have the parentheses here just so we could identify where the f of x was going, but we could take those off. This plus 1 and this minus 1 are going to add to 0 or cancel out. So that's going to give us the cube root of x cubed. A power and a root are opposite operations. So those are going to cancel each other out. And we're going to get x back as a result. Okay, so this is a formal proof to show that these two functions are indeed inverse functions. So we could say yes, they are inverse functions. Okay. So the next question maybe is, how do I find the inverse of a particular function? Let's take a second to look at that. To find the inverse, we could go through this set of steps. First, we need to check that the function we're investigating is one-to-one. We can do that by applying the horizontal line test. Right? We can make the graph, and I do want to show you some special things about the graph. Or now that we've done a lot of graphing, we could sort of visualize in our mind or with our graphing calculator what the graph would look like and mentally apply the horizontal line test, right? Okay, and then once we've decided that, we're going to replace f of x with y in the equation, and then we're going to exchange x and y in the equation. Everywhere where there's an x, we place a y. Everywhere where there's a y, we place an x. And then we're going to solve for y. So by doing this, we are sort of undoing each operation of the function f one at a time. And we're moving that to the other side of the equal sign, which is building the inverse at the same time. And once we've solved for y, we should have our inverse. So we're going to replace y then with f inverse of x. And then we can do a check, just like we just did, by composing them together to see and make sure, if we wanted to check ourselves, that they're inverses. Okay, I like to just continue to use the same example. I know we've kind of already discussed it a little bit, but I just want to show you the process, and this makes a really good example. So I'm going to use the same function f of x. I know we already know what the inverse is, but we'll just use this just to show you the process. Okay, so here's f of x. The first question is, we want to check to see if it's one-to-one. If you think about the graph for this function, I would like to graph it. Should we graph it now or later? I guess we could graph it now. You know what the cubing function looks like. What is this plus 1 going to do to it? It's on the outside of the cubing. so it's going to shift it up by 1. Okay, I guess we'll do the graph so that we can prove that it's 1-to-1, and then we'll come back and look at the inverse. How about that? Okay. So here's the graph grid. So we'll start with y equals x cubed plus 1. This one is not shifted left or right, so we could use that standard set of x values to make this graph. It's still centered at 0, 0. Well, I take that back. It's up by 1, so now it's centered at 0, 1. Okay, because it's moved up by 1. And we could plug all these in. So if I cube -2, I get -8, plus 1 would be -7. -1 cubed would be -1, plus 1 would be 0. 1 cubed would be 1, plus 1 is 2. 2 cubed would be 8, plus 1 would be 9. So if we plot these points, -2, -7, -1, 0, 0, 1, that's the center point, 1, 2, and 2, 9, and it's the cubing shape that we've graphed many times that shifted up by 1. Okay, so is this, round that out a little bit, is this graph of this function, is it 1-to-1? Absolutely. Passes the vertical line test and the horizontal line test. Okay, so yes, it's 1-to-1. So now let's take a second to find its inverse. So we said the next step, we're going to replace f of x with a y. And then we're going to exchange x and y in the equation. And then we're going to solve for y. So we want to get y by itself. So we're going to subtract the 1 over to the left-hand side. And then to remove the exponent, we're going to take the cube root of both sides. Now the cube root is an odd root, so we don't need the plus or minus here. And that's a good thing, because if we did have a plus or minus, it wouldn't really be a function. Okay, so we've solved for y, and now, because we're finished, this is our inverse function. Now we can replace y with f inverse of x. Just write it over here. And that's our inverse function. And if we wanted to, we could do the check. We just got finished doing that because we're using the same example twice. Okay, so I won't do another check here, but it would look just like we did in the previous page. Okay, so now let's take a second to graph this function so you can see how the graphs of a function and its inverse are related. So now let's graph y equals the cube root of x minus 1. Okay, to graph a cube root, we would like to use numbers so that when I subtract 1, I get a perfect cube. Now, it's not absolutely necessary. We can pick numbers that we like, right? And the calculator can do the cube root, but if you'd like to get nice round numbers, that would be a good tactic. Okay, we already know what the cube root shape looks like. What is this minus 1 going to do to the graph? It's on the inside, So this is a shift left or right. Remember, the left and right shift is opposite in sign of what we would intuitively think. So it's a -1, so it's actually shifted to the right. So the center point would be at 1, +1, because it's shifted to the right instead of at 0, 0. If I plug in 1, I get 0. So that's my center point right here. Okay, if I wanted to pick a number so that when I subtract 1, I get -8, because that's a perfect cube, -7 would work. -7 -1 would be -8, and then I can take the cube root to get -2. 0 would work. 0 minus 1 would be -1. I can take the cube root of -1 to get -1. Can you see a relationship between these two tables here? It's not a coincidence that these y values are going to make really good x values for the inverse. So 2 and 9 are also going to make really good x's. Okay, and when I plug them in, because the inverse performs opposite operations, I'm going to return to the x values I started with over here. So when I plug in 2, I should get 1. When I plug in 9, I should get back to 2. Okay, and that's not just this example, that's for all inverse functions. We can take the points that we have in the original function and flip them to get the points for the inverse. Okay, so if I plug these or plot these, I have -7, -2, 0, -1, 1, 0 is my center point, 2, 1, and 9, 2. Now we've said before that the cube root shape is like the cubing shape, but on its side. Now we have a chance to explain that. Okay, so when I flip the points like this, based on the fact that they're inverses, you can see that these graphs are very much related. So not only are their points flipped, but the whole graph is a reflection over this diagonal line where y equals x. This is very much related to the fact that the role of x and y are reversed for a function and its inverse. Okay, so let's summarize this a little bit. There are some special characteristics of the graph. Let me point those out here. Can't put it all on the screen at the same time, I guess. Okay, so the first one is the one that we just mentioned. Basically, this as a summary, it says I can flip the points, right? So if a comma b is a point on the graph of the function f, then I can flip it around, and b comma a will be a point on the graph of f inverse. It's always going to be true no matter which function we're looking at. Okay, the next one we just drew the picture of. The graph for the inverse function is a reflection of the graph of f of x over that line y equals x. Okay, and then the third one is a lot like number 1, but a little bit more global. So in number 1, we're talking about individual points, but also all of the x values for the original function become all of the y values for the inverse. And all of the y values for the original function become all of the x values as a group, right? That's the statement about domain and range. So the domain of f becomes the range of f inverse, and vice versa. The range of f becomes the domain of f inverse. Okay, that really is the better part of the story. Let me give you one more example because it's a little bit different so that you can see another one. Okay, so let's take this function. Let's say we want to find the inverse of g of x which is x squared minus 3, for x values that are greater than or equal to 0. Okay, so this is kind of an interesting example because if we think about g of x, let's ignore this addition at the end. Let's think about g of x as x squared minus 3. By itself, like this, it's a parabola shape because of the x squared, and it's shifted down by 3. Is that a one-to-one function? It's a function, but it doesn't pass the horizontal line test, so it's not one-to-one. Okay, so we need sort of a workaround to be able to find an inverse, because as it stands by itself, we can't do that because it's not one-to-one. We need it to be one-to-one because that way we can take those y values and map them back to their original x's. If two different x's have the same y, we can't map it back accurately, right? Okay, so we say that, all right, I can't find the inverse of the whole function, so let me just look at half of the parabola. So this x values greater than or equal to 0 are going to give me the right-hand side of the parabola. So if I cut the parabola in half and I just look at the right side of the shape, you can think about that shape. Is that going to be one-to-one? Feels a little silly, but yes, it would be. So let's draw the graph for this first, and then we'll come back and go through the steps to find the inverse. So the graph, or the function we have, is y equals x squared minus 3, and we're taking the x values to be greater than or equal to 0. Which means when I go to make the graph for this function, right, it would not be appropriate to pick x values that are less than 0, because remember, I'm only looking at the right-hand side. So 0 would be a good starting point. 1, 2, maybe that's enough. We don't have to fill in this whole chart. If I plug them in, I have 0 squared minus 3 would be negative 3. 1 squared would be 1 minus 3 would be negative 2. 2 squared would be 4 minus 3 is 1. Maybe that's enough. You could add some more. I think they would probably fit on this grid, but I'll just leave it at that. So this is a parabola shifted down by 3. So the center point is at 0, negative 3. And we're only doing the right-hand side. So then I have 1, negative 2, and 2, 1. Okay, so now that you can see this shape, I know it feels a little silly to take just half of it, but is this one-to-one? I think yes. It passes both the vertical line test and the horizontal line test. Okay, so now let's go through the steps to find the inverse. In the beginning here, we're going to ignore this extra part and just do what we would normally do with the function. Right, so I'm going to put in the y. And then I'm going to exchange x and y in the equation. Everywhere there's a y, I put an x. Everywhere where there was an x, I put a y. And then I'm going to solve for y. For this particular example, that means I'm going to add 3 over to the other side. And then I'm going to take the square root of both sides. Okay, in this case, we are taking a square root, which is an even root. So technically, we need to put in a plus or minus. In the end, we're going to end up removing, or actually choosing between the plus and the minus based on the domain we've chosen. So So we'll come back to that in just a second. When I take the square root, I'm going to cancel out the square. Okay, so as it stands right now, I have something that is actually not a function. I have the positive square root, and I have the negative square root. So this is sort of like that sideways parabola. Okay, so I would like to just use the part that's the inverse for my half a parabola. Okay, so this is where we bring in the fact that the domain and range are reversed for the function and the inverse. This is the domain for g of x. So let's write that down. So the domain for g of x is x values that are greater than or equal to 0. What is the range for g of x? I'm not writing an interval notation, although you could do that. I just want to make it as easy as possible to see the relationships going on here. If you needed to think about the range, you could look back at the graph we just drew. So let me pull back to that 1 second. So for the graph, the range would be bottom to top. So what is the lowest y value we have? Be down here at -3. So all of the y values for g of x are greater than or equal to -3. Okay, for the inverse of g, these are going to swap. Right, so the domain for g inverse of x will be the same as the range for the original function. So I need x values greater than or equal to -3. If you think back to what we've learned about square roots, right, the inside has to be positive. So the smallest number we could put in here would be -3. And that matches up with this. Okay, so that's great. The part that we really want to use is the range. So the range for g inverse of x is the same as the domain for the regular function. So the inverse function should have y values that are greater than or equal to 0. Which means when I'm evaluating this square root, I want it to come out positive. I don't want it to come out negative, because the positive is going to be the opposite of the original function I've chosen, right? My half a parabola. Okay, so since I wanted the y values to come out to be positive, I want to choose the plus and sort of get rid of the negative here. I told you we were going to make a choice, so we're choosing the plus. I'm going to write it as the inverse. So g inverse of x will be the positive square root of x plus 3. Okay, and I realize reasoning that out takes a little bit of practice. So I'm going to have some more for you to try out. You can definitely look online to practice this. But it's totally relies upon the fact that the domain and the range are swapped for the original function and the inverse. All right, let's finish this by graphing the inverse function as well, so you can see those two graphs side by side. So our inverse function looks like y equals the square root of x plus 3. If you wanted to put the domain underneath just to be symmetric maybe, since we have it over here, remember we said the domain is going to require x values that are greater than or equal to -3. And remember we said we could flip the points. So we could take all these y values and make them our x's. And if I were to plug them in, I should get the x values I see over here. And you can test that out for yourself. Okay, so if I plot those points, I have -3, 0, -2, 1, and 1, 2. And we've said many times that the square root function was sort of like a half of a parabola on its side, and this is why. We flipped the point, that's part of the reason, and it's reflected over this diagonal line where y equals x. All right. I hope that gave you a little bit of a picture of what inverse functions are and what their graphs look like in comparison to one another. Good luck with this. I hope you get a lot of practice. Good luck.